Hi everyone, welcome to Chemaholics, your one-stop channel to make chemistry simple, clear and exam ready. As I had told you in my previous video that I am going to record a video on some analytical chemistry related terms that are important in this part, and sometimes they can ask you about some objective type questions as well. So here comes my first term, which is simple. That is sample, a representative portion of material taken for analysis to determine its composition, structure or properties. A representative sample. Here this word is very important. For example, you have a reaction container like this. It may have an amount of 25 ml, 100 ml, 5 ml and so on. But you cannot take this whole sample to analyze it because every instrument have limitation of amounts. So in that case, we only take a small portion of this bulk material, small portion like either 100 microliter, 1 ml, etc., to analyze the sample, to analyze this whole reaction, that what is going inside this reaction mixture. We only take a small portion. So here are some aspects of sample that we need to know, like what is the purpose of this sample. Obviously the purpose of the sample is to know that what is going inside this reaction mixture. So means by taking this small portion we can analyze that what is going on behind in this reaction mixture. And these samples can be of very type. They can be solid, they can be liquid, they can be gas, biological material, environmental material, or any pharmaceutical, or any kind of material is there. But there is a condition that we can say a sample as a sample. Representative means this small portions should represent the whole bulk material, and so for that, and this sample should be homogeneous as much as possible, and it should be handled properly to avoid contamination. Like you are taking some sample, you are pipetting out, and if your pipette is not clean, and you have already pipette out something else by using that pipette, and you are using the same pipette to analyze this, then you are going to get a error based results that we all needs to avoid in analysis of any material. Now here comes another term, this is analyte. There is some difference between sample and analyte. Sample is what? The representative small portion. But analyte is what? Analyte is what we want to find inside this reaction mixture. For example, this is a reduction reaction. Reduction reaction of aldehyde. You are reducing it to alcohol. Okay. So, and obviously here are some catalysts. So what you want to analyze? You only going to analyze what? Aldehyde, that how much aldehyde is there in the reaction mixture, and alcohol, like how much amount of alcohol is formed inside the reaction mixture. And based on your demand, some people also find out like what is happening in the catalyst as well. Is there any change, or there are some techniques let's study about this in my further videos. I'm not going much deep inside right now. So we need to analyze what according based on our demand, that what we want to analyze. So whatever you want to analyze is known as analyte. And there are many professional societies which are specified for defining the instrumentation for sampling of a given material. Means every instrument have a specific sampling techniques, and there are many societies that is providing the instruction that for this measurement what kind of sample technique we should follow. Like in FTIR we use palette method. In UV we use solution state, and there are many more depending on the instrument. So these three are the societies that decide that what kind of sample preparation should take place for which instrument. And if a person is experienced and he know the statistical and he know how to prepare a sample can be a material can be sampled as accurately as possible. Means this is also a technique, this is also a art to prepare a sample for a specific instrument, because if this is not if something gone wrong with the sample, your whole data is going to be contaminated, going to be ruined. And obviously the sample preparation depend on the complexity of the sample, and the complexity of the sample further depends on the nature, like what kind of material is it. And there are some other relevant terms that is used for the sample. One is the gross sample. Here for example, like there is a field, for example there is a field, so this is what is gross sample. Yeah, for example you have picking this part, this part, this part, this part, and this part. You have taken these 5 spots, so these are batches, these are boxes, we can say these are the section of the same sample that you have taken, several parts you have taken. Then laboratory sample, then what you are going to do, you are going to utilize this, you are going to make it homogeneous, make it homogeneous mixture of this sample, and then after mixing it you can take a small portion of it. Okay, so what is this part is gross sample, and this is this is the gross sample, this is not, this is just batches after mixing the batches. And in this gross sample you are going to take a very small amount which is known as laboratory sample, and whatever you are going to identify inside the sample is known as analyte. Okay, so this is all about sample that I want to know, that some important terms that you should know about it. Then there comes the sensitivity. Sensitivity means every instrument have their own sensitivity, and based on that sensitivity we need to prepare the sample. So here sensitivity is generally nothing but the instrument response, the ratio of instrument response and the response toward the analyte. For example, let's say in UV you have prepared a solution of dye, okay, and you want to analyze its UV spectroscopy, but it is solution, it also has some solvent. For example, it has chloroform, and chloroform also has sigma to sigma star transition, and due to which it is also going to give you some UV signals, whether it is in the lower wavelength, but still it is going to give you the UV sample. Okay, so and obviously there are some air is also there, so that is also going to affect your data in UV spectroscopy. So for example, you are getting this data for simple solution, this is some noise is there, some response is already there, even there is no sample is present inside the UV chamber. But once you give the sample, it will give you something like that. So what is this? It is the ratio. This is the part, this is the response of the instrument, and this is actual stimuli. So the ratio between this divided by this is known as sensitivity. Okay, that small difference, and better the instrument, lower value this should be. Means even a small amount of sample, if for example, if I am for a technique, I have taken one normal solution and I have taken 10 normal, just an example. If it's not giving you any data, then it's give you a data, right? But in another instrument, one normal is giving you a peak, and another will be giving you a peak. So here instrument 2 is better than the instrument 2, because for the same concentration it is giving you a very good data. It is highly sensitive. So graphically the sensitivity is just the slope of the calibration curve. What is calibration curve? Of the calibration curve, like here you can take the concentration of the analyte, and here you can take the instrument output, and here the slope part is known as the sensitivity. Up here you can see that there are two instruments, A and B. At this concentration, the response from A instrument is low and response from B instrument is high. So greater the slope, greater the sensitivity of the instrument. So higher the slope, higher the sensitivity of the instrument. Now there are some factors that can affect the sensitivity. Itself, analyte has some certain part, like its own physical or chemical properties, like response of the input transducer, means what kind of input we are giving to the analyte, and composition of the sample matrix. So these are some factors that can affect the sensitivity. Here is another figure. You can see here this is not a straight graph. You are not able to calculate the slope value, but here is still you can see at the lower part you can draw the slope up to this part, and after that it's not. That means its sensitivity is changing. So this is a non-linear response, constantly changing the sensitivity. So here it's better to go with lower concentration. For example, if you remember the Beard-Lambert's law, in Beard-Lambert's law it is given for UV, and in UV we generally take the data from 0.1 absorbance to 1 absorbance. After that we don't record any data utilizing UV, because for example at this condition you will get like this, a peak like this, but if you increase the concentration it may be possible that you are going to get this, means the feature of the peak is going to be replaced, it become broadened, and it is difficult to analyze that what is happening inside the sample. So selecting the instrument based on sensitivity is also very important. Now there is a term called detection limit, or sometimes it is also known as limit of detection. The detection limit is defined as the concentration of analyte. Remember, analyte, concentration of analyte that gives the minimal signal. Similarly, let's say, and again take the example of UV. I have prepared a solution of 10 to the power minus 8 normal, 10 to the power minus 7 and so on. I have prepared it still to minus 3 and 1 molar, for example. For this and this, it may be possible that you will not get a UV signal. Then you will feel like that at 10 to the power minus 6 or 10 to the power minus 5 or 3 you will get the better UV signal, and obviously after that it may be possible that the peak is going to lose its features. So what is the limit of detection? For example, this is the value for 10 to the power minus 6. So this is the limit of detection for whatever the analyte is there. Below this the UV is not able to identify this. So this is simply what? This is the difference between black and the background. Blank and the background. Means background means the means when there is no sample, and blank is the sample. This is the signal of your analyte, and this is the signal without analyte. So this is the difference, and it should be 3 SB. SB is the standard deviation, and for standard deviation we need to take multiple data from the same instrument to find out. For example, standard deviation lies, you have taken the same sample, you are not going to change it, okay, and you are taking its UV data. What happened? It will give you like this, then like this. So here multiple samples we take, and you will find that in this area you will find there is some slight deviation from the same sample. So we need to calculate that standard deviation to find out the value of 3SB, and it should be multiplied by 3. So here actually what is the meaning of this 3? The meaning of this 3 is like, for example, you have a sample, this is the peak and this is the noise. Here if the height of this noise is, for example, 1 centimeter, then it should be 3 centimeter. Below it and above it should not be counted, it should be 3. So this must be this is the meaning of this 3 value here. So the lowest concentration of an analyte that can produce a signal distinguishable, which is 3 times the noise, it is 3 times the noise from the background noise. Okay, see here, this is again 3 times, this is the standard deviation and this is the sensitivity. So this is how we will calculate the LOD. For example, there is an example, there are 2 elements, element A and element B, and these are the absorbance signal. Okay, and both analyte have the same equal concentration is equal. Now sensitivity of the instrument system is identical, sensitivity is identical, again they are saying S is identical and concentration is identical, but detection limit of B is lower as compared to A. That means, see, even in here if you find out the ratio, its LOD is here is for example this is the area, for example whatever it is, and this is the signal area. Okay, for example this is 1 centimeter, for example this is 3 centimeter. Here you will calculate it, and here the gap is high, right? So the gap is high, so here this is the more sensitive one, B is more sensitive. That means if we decrease the amount, the instrument can analyze it. B can be detected even at a much lower value as compared to the A. Then there comes a term signal and noise. Like I told you before in previous slide, like there is a signal and there is a noise. Signal, output, when you have put an analyte into the instrument and it will give you a data, it will give you a graph, that is known as output response of the analyte. For example, in different instruments signals are different type, like UV has absorbance, and some current is the, maybe some instrument have current as a output, some have voltage, some have peak area. Okay, and proportional of the energy, and generally this value, like for absorbance, if concentration increase, this value is also going to be increase, the area is also going to be increase. And this is the part of the data that we want to maximize, this is the part that we want to maximize, like it should give us a good result. Now noise, like its output caused by the other component, like just like I told you in previous slide, like I'm dissolving dye in solvent, so solvent also has some output, so that output is known as the noise, that is creating noise, or any other for example any air or any instrument designing operational methods, something. So it is actually, this is unwanted part, we don't want the noise. Greater the noise, your signal is going to be sacrificed, but it's not possible for us to avoid the noises, it's going to be there because in the real world noise is there, we just want to minimize it as much as possible, and it is not originated from the analytes. For example, electric noise, like thermal, like in electricity heat is creating, environmental due to heat or environmental interference, electronic noise is coming, sample impurity, some impurity is there, your data is going to be changed, instrument fluctuation, for example light, because light fluctuation there, then there is some sensitivity or some random changes are there. So noise is random, we don't know how it is coming, and it limits the precision. Greater the noise, your precision is gone. So noise reduction is the primary consideration in obtaining a meaningful information during analysis. So we can only reduce the noise, we cannot remove it. So there are two principles for signal enhancement. Use the electronic hard devices like filters, we use filters, so that filters will filter the noise. or sometimes software is also helping to remove the noises. And post measurement means there are some mathematical situation like smoothing, and like post measurement there are some techniques to remove the noise, like subtracting the noise value. Signal to noise ratio. So the signal is what? The average signal amplitude divided by noise, average noise amplitude. Here for example, this is a data that I've taken. So this is the baseline. So here you will see that this is the part of the noise and this is the part of signal. And here you can also see there is also some defect is there. So which one is going to be good signal and bad signal? Which one has the good signal to noise ratio? So data is high, you can see the gap. This is the gap, and here the gap is low, and here this is the gap, almost same. So this data is poor, this data is bad, this data is good. So once the acquisition is over and electronic current is recorded, but yeah, that is important. Signal to noise should be instrument's ability to discriminate previously, because once you acquire the data, it is difficult to change the signal to noise ratio. We cannot change it by mere amplification and all. And higher the signal to noise ratio, more reliable, accurate and reproducible measurement is, and it is going to be lower. Lower means analyte signal may be hidden in noise and making detection or quantification unreliable. So greater, it should be greater. Now why it is matter? Greater the signal to noise ratio, lower is the limit of detection is going to be there. Lower noise, improve the detection and quantification. So that's why signal to noise ratio should be less. There is a question: if a spectrophotometer gives a peak height of this in absorbance for the sample and the baseline noise is 0.02 of the absorbance, like here 20, see 20, it's very high, 20 times stronger, it's 20 times stronger than the noise. So it is quite good data, it is going to be quite good data. So it should be higher as much as possible. Now there are certain types of noises, like environmental noise. Generally it originates from environmental external factors, like and they can be easily identified, and we can, by improving the instrument condition, environmental condition, we can improve it. It improves the transfer of energy to the measurement system from the surrounding. Okay, surrounding, we can do it by surrounding. It typically occur at the specific frequency or a narrow frequency of the bandwidth. And due to environment factor, there is some, means obviously around the instrument there is going to be some certain part that is going to be the common. So specific frequency is going to be changed. Two common sources of environmental noises are the electric and magnetic field, produced by the 60 Hz electric transmission line. Okay, this is the common. The other source of environmental noise is reflected radiant energy, means the energy we are giving, it's going to be reflect, so it is also going to create the noise. Mechanical vibration, because for example there is an instrument, you are vibrating something behind it, it's going to create a noise. Electrical interaction between different instruments, for example two instruments are very close to each other and both are on, and there's some electrical interaction is happening, so this is going to be a noise. So how can minimize it? Shielding the circuits from external source of energy, proper grounding of the equipment, and proper choice of the transmission frequency. So these are the way that we can minimize it. Fundamental noises, it is from fundamental or intrinsic property of the measurement system due to the discontinuous nature of matter and energy. Obviously during the instrument there is some nature is changing continuously within the matter and energy, that's why this is originating. So it will limit the accuracy, precision and detection limit. And it has further some parts, like thermal noise originates from the thermally induced motion of the charge carrier. Charge is carrying and there some heating is there, and due to which this thermal noise is opening, and it is also known as white noise. Okay, so this is the formula to calculate this white noise, where this is the average voltage due to the thermal noise. This is constant. T is absorbing, means temperature of absorbance, resistance, and band width of the measurement frequency. Now how can we reduce this? Reducing temperatures. Generally, when you go in a research institute, generally the instruments are put in a AC room. That's why, because so that the cooler is there, the thermal noise is going to be reduced. Narrowing the frequency width. The frequency width should be narrow, and it can be done by the software and when you acquire the data at that time. Next is the short noise. Originates from the movement of charge carriers across p-n junction. Generally, when we work semiconductors is there in every instrument. So due to the movement of charge, this happens, and it is signal dependent. It is depend on the signal, and this is the formula for the short noise. So how can, again, by reducing the width, bandwidth, and if large signal values are there, then it can be a problematic one. We will go into further in upcoming videos. Flicker's noise. Originate is flicker means we don't know where it is coming from, and generally observed for the low frequency. If the frequency is less than 300 hertz, it was generally observed. So this is the formula for that. So how can we should neglect this 1 by f term, and field effect transistor are more effective than the bipolar device. Okay, the magnitude of short noise is much smaller than the thermal noise and can therefore be ignored. So thermal cannot be ignored, but short noise can be ignored because the value is low. Flicker noise predominates in measurement, means if your measurement is between 0 hertz to 300 hertz, due to the contribution of 1 by f term, 1 by means frequency term, then it is going to be created. So obviously, okay, so this is the main problem. This is the type of noises. So with that, I will conclude this lecture today. Thanks so much for watching, and if you like this video and found that this video is going to be helpful for you, please share it with your friends, and do not hit the like button, and comment in the section what you want to learn more and what kind of improvement you want from me, and please share the video so that it can spread around the friends. So let's meet in my next video. Thank you so much.